Alright, hey guys, what's going on? So today we are going to be covering a derivation of the second part of our conformal algebra. In the first video, we derived most of these relationships. We're going to derive the rest here, and then we're going to get into something quite interesting about the dimensionality of our conformal algebra. Okay, and that's going to be later on for those of you who are members to the channel. Again, if you are not a member, you can go ahead and become one by going onto my Patreon page, where you can support there, or you can support by becoming a member here on YouTube. So without further ado, let's go ahead and get started on finalizing the derivation of our conformal algebra. So we're going to finish deriving this thing. We've derived everything that's circled up to this point, and so that's this right here. We derived this. We derived this one, this guy, and this guy. These guys now, we're going to derive. These two this one's relatively easy, so we're going to save that one for last. We're going to do, we're going to do these guys, and then we'll kind of sort of hand waving say just, these things are, the p mu and p nu are really just, it's kind of obvious that these things commute, right? Because their generators are this guy, and so when you do the commutation relationship between del mu and del nu, you see that it's perfectly symmetric, and that's going to go. So we can already basically just say, this is, we already know this. These two are a little bit less obvious, so we're going to go ahead and do those. Okay, so let's just remind ourselves again. We have our translations, our dilations, our rotations, and then these special conformal transformations. These special conformal transformations are really what make conformal field theory a conformal field theory. Everything else, without this, we don't really have a conformal field theory, okay? So if we don't consider these types of transformations, we don't really have a conformal field theory. We could say we have a weak conformal field theory, which is quite often said sometimes. That's when we usually say we have a weak conformal field theory, we're referring to a theory that just contains translations, rotations, and dilations, right? And so, and without even the weak part component to this, weak is sort of non-technical. It's a non-technical term here, but without conformal the special conformal transformations and the dilations, we are just dealing with translations and rotations. These are going to be translations in space and time, and we're going to have conserved quantities for those, right? We have total energy is conserved as you translate in time. Linear momentum is conserved when we translate in space, and then for the rotations we have the angular momentum. Those are all charges that are conserved under the guise of Noether's theorem. If you're not aware of that, we're not going to get into Noether's theorem right now, but that's something that we're going to sort of touch on later to sort of get a holistic perspective on conformal field theory. Okay, so let's continue. We're going to recall these identities we derived in the last video also. If you don't remember them, you can go to the first part of the last video that we covered on conformal field theory. And so with all of this, then we're going to derive the hard one first, right? This is our special conformal field theory with our special conformal transformation generator with this m alpha beta. Recall that the m alpha beta is this m right here, right? This m, which are these m's. These are the generators for our rotations. Here I labeled them as L, but these are going to be the generators for our rotations. Okay, so we have this then, okay, and then from here to here, then it's really just distributing all the way, right? We just, this guy with this guy that's here, and then this with this one is going to be, so we have squared, right? So squared with the alpha beta, that's this one, and then minus 2 times this guy, right? So this is this with this one, and then this with this one, which are these two guys right here. All right, and then expanding out even more, but this is just by rules of linearity and Lie algebras, is that we can take this guy out, right, and we get this guy here, right? So this guy here is this one right here, and these guys is this right here. All right, and then for this guy, then, right? So then we need to commute this mu nu with our del beta, and then the other two things will come out. So x alpha and del nu. Okay, so this one right here is really just this thing expands into this one. This thing's going to expand here. This one's going to expand here, and this one's going to expand here. Okay. All right, let's continue then. So there's a lot of math here, but we're going to go through this step by step. So then we have all these identities, right? These things came from here, right? So we take these commutation relationships, right? Nu beta, del nu x beta. We have del beta x alpha. Well, that's just going to be our this thing that we derived earlier on. This is our metric, okay? And there it is. Here's our metric. So you can kind of like just pause this if you want, because we have all of these commutation relationships we derived already, so we can literally just plug them in and we get all of this, okay? And then we see some things are going to cancel, right? We have, so from here to here then is just, well, we have x mu, x nu, and then this is going to contract to alpha, right? So this metric is going to contract nu to alpha in downstairs, right? So we get this term right here. And so we can do that for all of these terms, all right? You could pause the video if you want. We can do that for all of these terms, and we get this. And then we think things are going to cancel, right? We have x mu, x alpha, x mu, minus, and this is a plus, right? So things are going to cancel, and so reds cancel with reds, greens with greens, and blues with blues. And what we're left with then is this guy right here. Looks like we're getting somewhere, all right? This guy then, this can get, we just factor out a g mu beta, right? So here's a g mu beta, 2x alpha x nu del nu, 2x alpha nu, x nu del nu. Take the metric out of here as well, and we just do a little bit of index gymnastics here, right? So if this is a beta, this has to become an alpha for this to become a beta, and so forth, right? So these guys have a g mu alpha, g mu beta, so we can take out the g there as well. There should be a parentheses right here. So I will put a parentheses right there. All right, and then we have this guy here, right? So from here to here then, just multiplying out by negative, right? And then nothing here, everything here stays the same. And then from here to here then, we have negative I, g mu beta, right? So we're multiplying by -1, but by negative I then, right? So, and here's how this works, right? I times I is -1. Okay, -1 times a negative, that's going to be a positive, times another negative, that's going to give us this negative right here. We do the same thing here, right? And you can see how this works. But now what we're able to see is this here is just k beta. This is just our special conformal transformation generator, right? That's this guy right here. So what we end up getting is this. Factor the I out, we get this, and then just, I don't even know, this is just copy pasted literally. This is literally just copy pasted from here to here. And so we get the commutation relationship between our special conformal transformation generator and our Lorentz rotation, or our Lorentz transformation generator, right? Or our rotation, right? So this is M right here. I called it L, but this is also M, right? Because M, we said, is this right here, which is the same thing right here. Okay. All right. So moving on to the commutation relationship between the special conformal operator with itself, right? So we've done this guy. Now let's do this guy. All right. So k mu, k nu, 2x mu, okay, right, so we're just plugging these in, and we're going to plug and chug away now. So I've highlighted a few things just so that it is easier to follow. So orange, here's our orange bit, here's our orange bit. Blue, right, so this commutates, we're going to do commutation between this and this, that's this commutation relationship, and then between this and this, it's this one, then between this and this, then is this one, and then this one is blue and red and green, right, so that's this. All right, now I've highlighted, or I've underlined colors so we can follow the underlined colors as well. The underlined colors, that's going to be this brown one is going to expand into this brown guy here. This red guy is going to expand to this one. This green is going to expand into this, and this blue is going to expand to this. And we can see now, we just plug things in now, right? So this guy here is this, okay? This guy here is this one. This right here is going to be right here, because we have, let's see, that's going to be 2x mu sum over alpha, and then we have, let's see, oh no, wait, we have a 4. Where does this come from? So this guy here, these two guys, right? This is this guy and this guy here. That's these two guys right here. And then these two guys, this guy here is going to be right here. And then x squared dx beta, that's going to be beta nu, that's going to be this one right here. Right, so all of this then gets, we're literally just plugging our commutation relationships into, essentially what we're doing is this, right? We have this here should not be comma, right? So we have this thing commuting with this, which gives us all this, which is where we're getting all of these terms, right? Okay. All right, and then we see that a lot of this is just going to cancel, right? So because we have this, we have alpha, beta, right? So we have this guy here. So we have x mu x squared, right? So that is actually going to be x mu x squared. So that is this guy right here. And a lot of these are actually going to, some of these are going to cancel, right? Because we have, so this guy is this one. This one is nu squared mu. That's this guy right here. Right, so this guy is this guy, and this guy is this guy. And then this x squared x mu is coming from, we're going to have, we sum over, here we go, so x squared x mu, and then x squared x nu, right, so x squared x mu, x squared x nu, so these two guys right here, these guys, these are all going to cancel, right, because these are all pretty much the same term. I believe there should be 4s out in front of here. I think these should be 4s, and then everything cancels. I think what happened was I took my values of 2, and those should be 4s, right? So we have a 4 right here that came from this guy right here when we did the commutation relationship. So that's that 4. This 4 here, that's this 4 right here. So we've accounted for those 2 4s. All right, what's going, so this here, that's right, that should be a 2. This guy here should be a 4, right? This should be a 4. These should be 4s. So that is where these 2 guys are going to become 4s, and then things cancel. Okay. So we have the commutation relationship between k mu and k nu is 0. So we have this guy right here. This guy right here, as I said, that's pretty intuitive and easy. This guy here, I'll leave that as an exercise. I don't think I actually, well, it's not too difficult to see, right? So this guy here is going to be this right here, and m mu is going to be this right here. We can leave that as an exercise for you guys, for you to work that out. But what you get is that this is going to be 0. Okay? All right. So it's not too difficult to see that the generator of the translations commutes with itself. Also that, and so there we have it. This is our entire conformal algebra, and this has been derived now. So we have now derived every single colored term here, and that is our conformal algebra. All right. This is the backbone of conformal field theory, which will serve as the mathematical pillar for many other areas of study, ranging from string theory, condensed matter physics, statistical field theory, as we're going to see later. Really, what's going to happen is that we are going to be able to see that conformal field theory is, there's this weird phenomenon that happens in the mathematics of conformal field theory that basically says, there's going to be two sort of hidden extra dimensions to reality, okay, when you consider these conformal transformations, okay? And those 2 extra dimensions are going to be suppressed in a very interesting and unique way. And the only way we can really reveal these 2 suppressed dimensions is by considering, again, our special conformal transformations. Okay? So with that being said, we're going to talk more deeply into the mathematics about that now. And if you're contributing to the channel, you can go ahead and go into the full video of this and see that. If you're not, you can go ahead and become a member and then get access to that. Okay? So with that being said, let's go ahead and move on to the member payment stuff.